This is special products of polynomials. There are some polynomials that we can solve without having to do the distributive property, without making a table, and without using the FOIL method, because they have certain patterns that always repeat. So if we know the pattern, we can easily solve the problem without using any of those other methods. One of these patterns we see is if we have two terms that we're adding and we're squaring that whole entire set. So if I have a plus b, I'm adding two terms and squaring that. I'm always going to end up with the first term squared plus 2 times both terms plus the second term squared. So for example, if I have x plus 5 squared, x is my first term, 5 is my second term, I'm going to end up with x squared plus 2 times x times 5 plus 5 squared. Or simplified, that is x squared plus 10x plus 25. Now, if I'm subtracting two terms, I'm finding the difference of them and squaring it, it's going to be the first term squared minus 2 times both terms plus the second term squared. So if I have 2x minus 3 squared, it's going to be 2x squared minus 2 times 2x times 3 plus 3 squared. Or simplified, it would be 4x squared minus 12x plus 9. Let's try a couple of these using the shortcuts. So here I'm adding two terms. So in order to simplify this, in order to square this, it's going to be my first term, 3x squared, plus 2 times both terms, 3x and 4, plus my last term squared. Now I'm going to simplify this. I'm going to get 9x squared, because I'm squaring both things here in my term 3x, plus 24x plus 16. Here I'm finding the difference of two terms. So in this case, it's going to be the first term squared minus 2 times both terms, 5x and 2y, plus the last term squared. So this is going to become 25x squared minus 20xy plus 4y squared. Another pattern we see is if we are multiplying two terms that are being added and then the same two terms being subtracted. That will turn out to be the first term squared minus the second term squared. So if I have x plus 3 times x minus 3, it's going to be the first term, x squared, minus the second term, 3 squared, or x squared minus 9. Let's try a couple of these. So when I see it's a sum and a difference of the same two terms, it's going to be the first term squared, t squared, minus the second term squared, 5 squared, or in this case, t squared minus 25. Here my first term is 3x. It's going to be my first term squared minus my second term, y squared. So here I get 9x squared minus y squared. We can also use some of these special product patterns to do simple math problems. So we've got 26 times 34, and something I notice about this is 26 is 4 less than 30, 34 is 4 more than 30. So I can actually create a problem that I can solve using some of these special product patterns. So I can rewrite 26 as 30 minus 4. That equals 26. And 34 can be rewritten as 30 plus 4. So basically here, I have a sum and a difference pattern. So it's going to be my first number, my first term squared, minus my second term squared. So 30 squared is going to give us 900. 4 squared is 16. So when I subtract, I get 884. So the product of 26 and 34 is 884. Now let's look at a real life problem. A combination of two genes determines the color of dark patches of a border collie's coat. An offspring inherits one patch color gene from one parent, but each parent has two colored genes, and the offspring has an equal chance of inheriting either one. So let's say the capital B gene is for black patches, and the lowercase r gene is for red patches on your border collies. And we're going to suppose that each parent here has the same gene combination, BR. They both have black patches, but they have the gene for black patches and one for red. Black and red. Now the black one is dominant, so anytime that we have the capital B in our combination, the dog is going to end up with black patches. So in this case, when we're looking at this Punnett square of all of our possibilities, we've got dad's combinations here, mom's here. We see we get double B is a possibility, B with an R is a possibility, another B with an R, or two R's. So since every time you get that capital B, that black gene, the dog is going to have black patches. 75%, 3 out of 4 of our dogs here, 3 out of 4 of our possibilities are going to result in black patches. That's 75%. 75% of the dogs from these parents are going to have the black patches. We could use a polynomial to model these gene combinations. So we know in this case that both parents are giving you a 50% chance to get the B gene and a 50% chance of getting the R gene, and it's squared because in this case we've got mom and dad giving you this possibility. So if we follow one of our special product patterns, when we're adding two terms, it's going to be the first term squared, so 0.5 times b squared, plus 2 times 0.5b times 0.5r, plus our last term, 0.5r squared. Now if we simplify this, 0.5b squared is going to give us 0.25b squared. 2 times 0.5 times 0.5 is going to give us 0.5b times r. And 0.5r squared is going to give us 0.25r squared. So basically, we have a 25% chance here of getting the B squared, 2 large B genes. A 50% chance of getting a large B and an R gene in our dog, and a 25% chance of them getting the double R, R squared, which is exactly what we see in our Punnett square.